Alright, so this is Physics Lab 3, where our objective is to find the mass of a black hole given the position data of a star caught in its orbit. And I found the mass of my black hole to be 3.7812175 times 10 to the 31st kilogram. So here are the models we're going to use for finding the black hole. We're going to have, given 3 consecutive data points, we'll be able to find dp/dt of the star, and this will be equal to Fnet because we're going to assume that the only force acting on the star is the gravitational force of the black hole on the star. Therefore, this Fnet that we find, we'll be able to put this into the gravitational force equation. So Fgrav will just be equal to the Fnet, and we're also given the mass of our star and the position of our black hole, so we'll be able to find R by subtracting the position of the star from the position of the black hole. So this is my code that I used to find the mass. We have our initial star mass, which is 2.3514 times 10 to the 27 kilograms, and our delta T is 86,400 seconds, or 1 day. Here is our loop that we'll be using. So we take the position data of our star, and for every 3 consecutive points, this iteration will calculate the velocities of our star, and we'll multiply these velocities by the star mass to get the initial momentums and the initial and final momentums. And from this, we'll be able to calculate dp/dt by dividing delta p by delta t. And then again, we're going to set Fnet equal to dp/dt here because we're going to assume that the only force is the gravitational force. So here is where I actually find the mass of my black hole. As you can see here, r is the distance between the 2 objects at any given data point, and g is 6.67 times 10 to the negative 11. And we arranged our gravitational force equation from here to solve for the mass of the black hole here. So one thing that the code... See, let's run our module first. So here's the path of the star. Fnet is this yellow arrow. Fnet parallel is the black arrow, and Fnet perpendicular is the blue arrow. As you can see, these 2 arrows, the black and the blue one, are perpendicular to each other. And if we add them up, we find that they do indeed add up to the Fnet arrow. So one thing that this code doesn't account for is the changing distance between the 2 objects. R changes with every iteration of the loop, so the mass of the black hole is going to change. Because of this, I calculated the average of all of the masses that our code found. There were like 1,000 masses. So I took the average of them and found my result, 3.7812175 times 10 to the 31st kilogram. And we have a standard deviation of 9.29738 times 10 to the 26. And for objects that are this large, this is a really good standard deviation because it's actually pretty small compared to how large the mass of the object is. Alright, so what does this mean? dp/dt is not going to be always equal to Fnet here because dp/dt is the change in momentum of the star, and then Fnet is the gravitational force on the star by the black hole. And again, these 2 aren't equal to each other because there could be other forces acting on the star that would augment its position data that we might or might not be able to calculate. And then what if we replace the existing black hole with a new one? but the star position data remains the same. I think that the mass would still be the same because, again, since the star data will be the same, our methods for calculating FNet will be exactly the same. You know, the values will be the same, and then when we input that FNet into our gravitational force equation to find the mass of the black hole, since the numbers are the same, it's not going to give us a different black hole mass. Alright, so that was Lab 3. Thanks for watching.